Thank you for joining. We have a really, really good session for you today. Let me introduce myself. My name is Gad. I'm the founder of TensorOps and CTO, apparently. These days, we are a consulting company. These days, we're really in the hype of the AI, trying to help companies build AI solutions on top of their environments. We work with some incredible companies like Notion already, Lytron, JFrog, companies that you may know, companies that you may not know, but never mind, you'll get to know them maybe someday. I have today with me Gabriel, who is one of our senior engineers. How are you doing, Gabriel?
Hey, good. Great to be here.
So we wanted to speak today about cost of doing AI for less, because we do notice that cost is really becoming one of the most interesting topics as AI applications are getting out of the garage towards production. And what we wanted to discuss is about three main topics, right? One is, what does it mean, cost in an application? Why is it so important? We're going to go over it quite quickly. And then we're actually going to talk about how to navigate the cost versus fitness trade-off, or cost versus fitness landscape in AI applications. And eventually we're going to focus on method and techniques, which is going to be the main part of this session. So why is AI different from other software applications? Because effectively AI is just software, right? And just like backend is not the same as front end, and just like mobile development is not equivalent to developing application for desktop, AI is different. But AI is also different from traditional software in a way that it can do autonomous decision making, or it can do it has predictive capabilities. And another thing that's really different with AI, in our perspective, is that cost is a dimension. And what do I mean by cost is a dimension? So as I told you, we are a services company building AI solutions. So we already built a few solutions for customers. And what I did is that I went to ask my team, can you give me some examples to how much does it cost to run the workloads that you build for the customers, right? So for example, if you build a solution that's based on AWS Lambda, which if you don't know, it's like this serverless service that what it allows you to do is to basically host very simple functions or very, very simple servers on AWS, and ask them, how much does it cost to run about 1 million requests? Now, these are not like very well-established statistics, right? Because you may get a bit of a different number up or down. This is not based on enough numbers to get statistics, but I think it is a fair representation to give a sense to why cost in AI is so important. So Lambda, for example, 1 million requests is going to cost you $5. And if you're adding to it a database like Cloud SQL, then you're around about 200 requests at $200 per 1 million requests. So think about myself. I want to serve 1 million times that people are going into my website. And let's say each and every one is making just one request, then the whole cost of hosting this website is going to be $200, which is not a lot of money at all. Now, if I'm adding a little bit of AI to it, like the Google AI Vision, for example, for face detection, then we're talking about $1,500. But when you think about AI, really, like these days, you're thinking about chatbots, right? Like 3.5 agent or GPT-4 agent. Now, when you go to 3.5, an example of an agent that we built, we find that it costs 50,000. And again, maybe in your case, it was a bit different. Maybe then the numbers are different, but I just want to give you a bit of a sense. What's interesting, and you know, the obvious thing here is AI is expensive. Thank you very much, Captain Obvious. But I don't want to focus just on the bad part of AI being the bad part of AI costs being high, but actually talk about the opportunity that's here. And the opportunity lies here, right? So as it turns out, this GPT 3.5 agent and the GPT-4 agent are actually the same application, right? And how can that be? So very often what you do in LLM applications is that you have a Python app that a developer goes and writes. Maybe it contains some kind of a LangChain code. And then that LangChain code is going to make calls to an external LLM, to GPT 3.5 or GPT-4. And you can switch between GPT 3.5 and GPT-4 quite easily. And so with the same application, you have the opportunity now to decide how much you want your application to be smart, right? Because when you're going to GPT-4, your AI application is going to be much more expensive, but it's actually going to be also more expensive, but more smart. So I don't see the cost of AI application as just being a burden, but it's also an opportunity because uh, based on how much you're willing to spend, you can decide if you want to go to the store and buy an Einstein or some smart guy that is not an Einstein, right? Based on the budget, you can decide, like switch it like a volume switch and decide how much your application needs to be smarter. And um, the orders of magnitude between applications. So this is a great example from that I found recently on LinkedIn. So the differences between LLM applications can be in orders of magnitude. Sometimes 2x, 3x, 10x, and sometimes 1,000x between really advanced models and really small models. So one thing is, yes, you have a huge opportunity to reduce costs, but also you have the opportunity to go up if you want. And this is a notion that I think you're gonna see throughout this webinar. Now, if you're already talking about Notion, Gabriel, so how can I intuitively leverage the fact that these models are have a different have a very different pricing?
Yeah, so it's not like you can just pick a model because it's cheap. That's not the point here, even though you would save a lot of money, but obviously the results wouldn't be great. Here's where we introduce the concept of benchmarking models. And here in this table, this is a very common benchmark. It's uh, LLM leaderboard from Hugging Face, and they just measure all the open models. And you can see here that the best model isn't the best model at every benchmark because these benchmarks are applied to different fields. So one of them is maths, the other is question answering, the other one is specifically designed so that humans are better at it than LLMs. So you need to pick a model that is, yes, cheaper, but also somewhat relevant for your specific use case. Another really cool thing that a previous client of ours did was to, instead of trying to make their models extremely smart and they use GPT-4 for everything, what they did was they restricted what their users could do with LLMs. So in this case, they defined six possible interactions that you could have with LLM in terms of creative writing. And if you narrow down this scope, the user experience is a lot more controllable. And hypothetically, what you could even do is each of these six buttons could send a request to a different model that you specifically trained to be doing this one task very well. And these models could be much smaller and therefore much cheaper. So again, tell me a bit about how we can use cost as a differentiator in this current market.
Yeah, so let's take, for example, things. The case of Klarna. So Klarna is a wonderful company. What they managed to do is they said, using AI assistants, we managed to do 2/3 of our customer service chats in the first month. Now we don't have the Klarna information, so we don't know exactly what goes behind the scenes. But let's say that the human support used to cost $25 million before applying AI. Now, imagine the first AI solution is GPT 3.5 or Gemini 1.5 Turbo, and then the cost of it, as it turns out, $1 million. And then they tried another version, which is with a smarter LLM, and the cost went up to $10 million. So, right, if you want to start to get the sense of saving money with LLMs, then you may think that, oh, right, so here's an opportunity to save $24 million, but that's, of course, a very partial representation of the problem, right? If you really want to think about the cost reduction that you're going to experience, then you actually have to look at how much human work is going to remain after you apply that AI. So let's say that in the case of the first chatbot, after applying $1 million of cost to a GPT 3.5 model, they had 10 million more to pay for humans to do the work. And in the chatbot, which is more smart, then humans had less work to do, and then they only had to pay $5 million. So effectively, when you're measuring the cost of your AI application, you also need to measure the effective reduction in human labor, or in the other effect that you're trying to achieve, in the automation that you're trying to achieve. So in this case, for example, solution A is indeed better because you managed to do the same thing with $11 million, even though you still need to pay more to human support as opposed to the first one. And if you only looked at how much cost you're saving in human labor, maybe you would have gone for solution number two. So this one is to show you that monitoring the cost of LLMs just not goes beyond just seeing how much you're paying for a OpenAI or a Google Cloud. So
So
yeah, Gabriel, just sorry, just a question like, so far we gave people intuition to how they can measure or what's the importance of doing cost reduction for LLMs. How can you effectively impact the cost of your bill? How can you effectively start to reduce the bill?
So I'll be a bit more negative and start by what you can't control. So we all saw that GPT-4 is about 20 to 30% of the cost that it was when it came out. And we're all very happy that it got cheaper. But the reality is this we can't provide value by using this because it gets cheaper for everyone. So this happened because of hardware advances. So NVIDIA keeps releasing better GPUs and selling more of them, and algorithms keep getting more efficient. So the GPT-4 model keeps getting better. It runs even less weights. It keeps getting better in ways that we can't even comprehend, but we can't control this. So it's useless to us as a way to provide value to our users. But there are things we can control. So these two things are mainly local optimization, and this is basically the way that we use these models. So send less tokens to the model, try to send less requests, or architecture design, which is kind of the encompassing software around our models so that we avoid sending unnecessary requests and we make it as optimized as possible.
I want to jump in, by the way, and say that, sorry, I want to jump in and say that if people have questions, you are more than welcome to drop them in the chat or in the Q&A, and we'll be happy to answer this. So while Gabriel is talking, I'll be answering some questions and so forth. So do feel free to jump in with your question. We'll be happy to address them.
Um, so I want to start by local optimization. And the first thing that comes up here is that we said we can pick smaller models that are cheaper. So what does this mean? So we're defining model size as the number of parameters. This is not a metric that is absolutely comparable. Some 10 billion parameter models are going to be faster than 15 billion parameter models running on another machine, but it's a good metric to kind of keep in mind for the levels of knowledge that these models can have. The rule of thumb for these models is that bigger models tend to be better at generalizing their tasks. So we see that GPT-4 needs a lot less context to perform a task that it never heard about. And a very small model will need a very narrow scope. And this kind of leads us to the conclusion here that if you want to reduce your costs, you'll probably want to reduce the size of your models. And there's two things you can do, and you can't get away from this. You'll either narrow down the scope of your application, or you will be giving up on some accuracy along the way.
So it's interesting. Can you go back to that one? So effectively, what I think we saw is that these are the main two trade-offs that you're going to make when you're going to uh, build LLM applications, right? Either you're going to make your LLM more narrow. So my LLM cannot do math. It cannot do, generally LLMs cannot do math, but maybe my LLM cannot do summarization and my LLM cannot do a generation of stories, but it can do really, really well extraction of specific knowledge or formatting. Or you're going to say my LLM it still has broad set of skills, but it has less accuracy. So really, really interesting.
Yeah, no, we see this all the time where very small LLMs outperform GPT-4 in extremely narrow context. So this is how powerful it can be.
Mhm.
Yeah, so I'm now going to talk a bit about a very common technique to improve performance of the models. Of course, this is not just about performance, but also about, so if you improve the performance of a smaller model, you can use this as a cost reduction technique as well. So An example that we like to use here is the emotional prompts. This is a prompting technique that essentially just adds emotional cues to your prompts, and a lot of researchers found out that LLMs respond well to emotional prompts, and it increases the accuracy of your responses by 10 to 20%. Nothing crazy. It's not going to make GPT-3 become like solve all of the world's problems. However, what it does is it kind of exposes this correctness graph that we're seeing here. So GPT-3's correctness has a bit of an overlap with GPT-4's depending on the prompt. So if you have a very, very good GPT-3 prompt, let's say emotional prompt and all the prompting techniques, it will perform about as good as a GPT-4 out of the box. And this doesn't seem that exciting, but when you think about the price difference between GPT-3 and GPT-4, which is about 10 times as expensive as GPT-3, you can see that there's a huge amount of value that you can provide here by simply doing better prompts and using a smaller model. And this is kind of what we did with another client of ours. So this is Panaya, they're part of Infosys, and we wanted to summarize a few SAP system notes. These are very dense notes. They're terrible to read because they're like a lot of small like acronyms and things that no one understands. But by summarizing them with LLMs, they can be readable in 2 to 3 minutes, and people maintaining these systems can do it better. And we found out that GPT-4 out of the box was almost like this all-knowing entity that could summarize anything. But it was expensive, it was slow, it wasn't that great to deal with. But GPT-3, with a very, very good prompt, was just as good. It took us a bit longer, but now we have an application that is faster and cheaper. And another example of this type of development of prompting engineering techniques is the chain of density prompts. This is developed by Salesforce, and I don't want to focus too much on the papers, but it's basically you expand your summaries iteratively by adding new context, by adding new words, like new keywords. And this makes a lot more calls to the model, but it allows you to use much smaller models and therefore save some money on not using GPT-4.
Carol, I want to jump in because this is not a webinar on improving model accuracy, right? So we did have a great webinar about prompt engineering techniques and how you can get the most out of your LLMs. So obviously all of these techniques in which you're doing prompt engineering also introduces increasing tokens. And I think your next slide is going to talk about, because, okay, I understood the basic idea, right? That if you are taking this LLM and you're doing really good prompt engineering, so you can go down from GPT-4 to GPT 3.5 or from a bigger model to a smaller model and get the same accuracy because you're doing really good prompt engineering, but then you're paying more because you actually introduce more tokens. So, if these like prompt engineering techniques, very often you use few shot and you use a lot of techniques that are going to add a lot of tokens to your input. So every time you're actually sending more tokens, how can you actually go back and fix that?
So a very good example of how to reduce these tokens is to use some kind of compression of your prompts. The one that I wanted to talk to you about here today is LLM Lingua. So this is a technique that basically trains a model to decide whether a token in the prompt is relevant or irrelevant. And what researchers found was that most of the words and the way we speak English are completely relevant to LLMs, and they can be completely removed. And here we can see that we run it through this model, and then in the end, hopefully sometime soon, we get a result which is much smaller, but that theoretically will have the same effect on the LLM. So we won't be losing any performance at all. It's just going to become faster and cheaper. So this kind of counteracts these very big prompts that we make. And so this is just the explanation of how it works. They train a model to classify every token into relevant, not relevant, delete the irrelevant, and then compress it, and then do the same thing you were going to do with the prompt afterwards.
Yeah, so I want to talk about the elephant in the room, because when you're talking about LLM cost reduction, it's always about how can I pay less for achieving the same level of accuracy I had before, right? So if you want to talk about achieving the same level of accuracy or achieving the same performance of the same fitness to my problem, I actually need to speak about how to do evaluation. And one thing that is very, very tricky with LLMs is that the evaluations are very, very not trivial. Sometimes, for example, for the benchmarks, you're actually using a more expensive model. So in many of these like scoring tables, scoring leaderboards, you are using the most advanced model to evaluate the accuracy of the other models. So that's kind of stupid if you're in your system. Sorry for the harsh words, but if in your system you have to, just to validate that you're doing something right, use a more expensive AI, then you actually haven't saved anything if you reduce the size of the model. So let's talk a little bit about evaluation to give you a sense of how can evaluation still be effective if you are if you're trying to reduce costs and not pay for it too much, especially since a lot of the evaluation is actually done by humans, right? So if you want to get, and Gabriel's going to mention it, if you want to get like really, really good evaluation, you effectively have to expose the results to human beings. So Gabriel, give us your 2 cents on evaluation.
I certainly have a lot to say about evaluation, some more controversial than others, but the starting point for your evaluation is usually this table that we showed you previously. So you look at a table of models, a bunch of scores, you pick the highest score and you use that one. And this very quickly kind of became a game to people developing these LLMs. So it's a very good starting point, but we can't just do this. It's not enough for us to just use these benchmarks and then call it a day. You're not going to provide much value this way. So another type of benchmark is like Gad was telling you about, so human evaluation. So in this case, this is Chatbot Arena, and basically users are presented with two possibilities generated by two different models, and they pick whichever answer they prefer. And what we see a lot is that most of the times, new LLMs will tend to outperform everything in the benchmarks, but you get to the human evaluation, this is where it really comes to it. And most of the times, the bigger models tend to perform here, and OpenAI tends to perform much better. So there's a bit of a disconnect between benchmarks and human evaluation. So this kind of brings me to want to define with you, what's a good evaluation? And a good evaluation is always whatever is closest to what your users would think. This is the whole point, right? So if your users think that evaluating your new model in a worse manner, then it doesn't matter, right? So a technique that people try to use to approximate human evaluation is to use LLMs. LLMs in a lot of ways think like us. So the logic is that if you use a very smart LLM and ask it which of these answers is best, it can probably get it right. But what we're starting to find with newer and newer research is that LLM as judges tend to correlate better with non-experts in the field in question, and not as well with experts. So we can see here in the plot, and this is a very recent research that came out, even GPT-4o only has a correlation of not even 0.5 with real human experts. And this is quite dangerous because it's not perfect at all, right? So there's kind of a gap here. And this is the gap that the new concept of foundation evaluation large language models are being trained to fill. So we defined that we want to be as correlated with human perception as possible. And people are now developing models that are specifically trained for this purpose. So they're trained on pairs of outputs, and they try to optimize to be as close to what a human would say is the best one as possible. And this is the concept of the new Galileo Luna foundational model, which is already outperforming all GPT models on evaluating so an LLM as a judged workflows, and it can be further fine-tuned on your own evaluation data sets so that it correlates better with your users.
Yep. Just before jumping into this one, I am seeing from Marcus a question here about what can you do when you're not sure if the AI is going to achieve the results that you're going to get? We have a slide on that later, so I'm going to keep your question for later. And if you have more questions, by the way, drop them. And we will make sure we answer them either through this webinar or throughout this webinar, or through the slides, or through talking to you. So yeah, Gabriel is basically saying, in order to really evaluate if your LLMs are, if your LLM application is doing well enough, you need to go to the humans. This is, of course, the most expensive way of evaluating. And then you see these like specialized LLMs for doing evaluations, that it actually turns out that in order to evaluate if your LLM application is doing well on a specific task, you can use actually a smaller LLM that is specialized in doing that. But the problem is that not necessarily it's going to be very, very much correlated with humans. So what you can see is the question, how are you going to validate the validators, right? How are you going to validate the evaluators? And one thing that you can see is this great work from very recently, 2024, that shows that you can calibrate on occasions your validator, so it would fit the expected behaviors of your users or of your human labelers. So in that way, you're leveraging the fact that humans can calibrate with very few examples the validator, and then you're using the validator to go against your more bigger data set or more data. So I like that research quite a lot. So we talked a little bit about doing the evaluation. Now let's get to some more techniques about how to actually reduce cost. And if you need to talk about reducing the cost of LLMs, you're probably going to talk about quantization, right? So when I'm talking about quantization, Gabriel mentioned before that the more parameters the model has, it becomes more capable. And there was a question here in the chat. What happens when you're going to a smaller models? You're like losing a little bit of the generalization of the model, and that's very much accurate. So the more parameters you have, the model is more capable. But the number of parameters is not the only critical factor that's going to determine. So these parameters are effectively numbers, right? Typically, they're 16 bits. They're represented by 16 bits. What if I could take this 16-bit number and just use less bits to represent it? Now, quantization is not what you see here, right? It's not that you just trim the floating point at a certain point and just keep it like that. It's a more statistically heavy process. But this is actually a fair illustration because it shows you that what you're effectively going to do is you're going to take big numbers that go in these parameters and represent the same parameters with significantly smaller numbers. Now, what is it going to do to your LLM? Well, first of all, let's see the results. Whenever you're hearing of, I managed to run this LLM within my browser, or I managed to run it from my MacBook, and I got very, very low latency, these are the results that you're getting. I need to find a source for that because I took it from Twitter. But this is a great example. Oh, yeah, it actually shows down here. This is a great example to how you can build really, really fast LLM systems that can be deployed on premise on your MacBook inside the browser that give you really, really, really quick and quite accurate results. So quantized models are the basis behind all of these demos that you're seeing about really lean LLM systems. Let's give you a little bit of intuition to how it can work. So here's a list of the Llama 2, 7 billion, 13 billion, and 70 billion parameters. And you can see that what's the size of the, I would say, foundation model before the quantization. So you see that you are starting from 13 gigs and you're going up to almost 140 gigs. And 140 gigs is bigger than whatever GPU you're going to find out there available to the public. So if you want to host a Llama 2 70 billion parameters in its original parameter size, you're actually going to have to split the model into several GPUs. And of course, that makes the price significantly higher. Now, going to the right, to the quantized size, you actually see that the size is reduced dramatically. And even the biggest Llama 2 that you have here, the 70 billion, is only 40 gigs. And you actually have GPUs that can accommodate just this single Llama 2 70 billion parameters. Now, the obvious question is, what is it going to do to my accuracy? So what Meta found is that actually you should go probably for more parameters with less precision, right? If you measure this on benchmarks and on real life tasks, these quantized models are actually doing better than models with more parameters. Models with less parameters that have full precision. So that's quite interesting because the effect of it, this is, for example, a service from AWS called Jumpstart. And you can see the difference between the 8 billion and the 70 billion on the Llama 2, Llama 3, sorry. So you can see that in order to host the smaller model, which is full size, you're going to pay 3,000. And when you're going to go to the bigger model, you're going to pay 23,000 per month for that machine with that many GPUs. So effectively, if you can reduce the size of the machines that you need for hosting, you're going to see a reduction in at least an order of magnitude, as you can see here. Or in this one, it's almost an order of magnitude. I do want to speak about a misconception that is very often associated with quantized models and hosted your own LLMs. So Eugene Yan is one of the greatest consultants of LLMs. He recently wrote a blog post about the lessons that he's learned from a year of applying LLM applications. And he's saying, obviously, before you're getting to production or before you are developing, you have big traffic, you do not use GPUs. You always go to managed service. Managed service being GPT-4o or Gemini, these hosted LLMs. And the reason is quite natural. Like people think, of course, when I'm just paying when I need the LLM, this is significantly cheaper than setting up an instance, having it not very utilized, and then of course, like the upper way in which you see, like I'm paying very little for every request that I'm making versus scaling up and down this Hugging Face model that I hosted. Now, what we found is not necessarily that when you scale up, you will actually save money by hosting your LLMs. This is not true at all cases. So it can be true, but not at all cases. And why is that? Because these models do not scale very well, it's hard to make parallel requests, and still, even if you quantize models, it's quite difficult to put a lot of models on the same machine and utilize them very well. You will see that you will not see, even at a fairly nice large scale, the scaling of the system is not as efficient as what probably OpenAI is doing. So I don't know if OpenAI is just losing money on their hosted LLMs. I don't know if they're doing something really smart behind the scenes. But from our experience, even in larger scale, it doesn't mean that quantized models are going to be cheaper than hosted LLMs. When is it going to be cheaper? So as again, the dimensions that you have to look at when you're doing LLM optimization or LLM application optimization is not just cost versus how much I want availability, but also against the task. This OpenAI model is a general purpose model. So it has the ability to do a lot of tasks, whereas the quantized models is typically used for cases where you can narrow down the task. So when you're already comparing narrow, small LLMs that are limited in their ability, then in this case, yes, you can get cost reduction. So it's not, I would warn you from having too many hopes that a quantized model is going to be more cost efficient than a GPT-4o. These managed services typically for general purpose are more efficient even in higher scales. When you're talking about specialized tasks, however, you can see cases, for example, like BuzzFeed. BuzzFeed said already, I think more than a year ago, that they managed to reduce 80% of the cost by using a self-hosted LLM fine-tuned to a specific task. But it's really important. They even said in their blog post that it's compared to the general purpose LLM. So that is one thing that I think you should come out with from this webinar. So we talked about that local optimization. And when I'm talking about local optimization, I'm talking about the way that you interact with a single LLM, right? How can you write the request? Is there prompt or go to the single LLM that is cheaper? Now, very often you saw that these decisions are not standalone. When you're building an LLM application, you're actually building an architecture around it. So what are the architectural decisions that you can make in order to reduce costs? And one of the things that you will see, like we mentioned in the Notion case, is that your LLMs can be defined to perform several tasks. For example, summarization or expansion or bulletize. And once you know which task your LLM is doing, perhaps you can route the task to the right LLM. You can have multiple LLMs that are doing very specialized tasks, and by that you're reducing the cost, because maybe one needs to do calling math functions, and now one needs to help you do coding, and another one needs to do interact with different languages. So there we go. Next one. So there is this company called Martian, for example, that offer their own design pattern that you're going to see. It's called a router. And the router is allegedly supposed to give you results that are GPT-4, but for lower cost and better latency. So the idea of routing the request to the right LLM is already something that we're seeing being commercialized. And you should definitely look at these kind of solutions. Now, you're not necessarily going to go and send all of your data to a commercial model router. Some people want to implement that. And I did say I'm not going to talk about local optimization. I'm not just going to talk about how to interact with the LLM in a more efficient way. So why do I call it an architectural decision? I call it architectural decision because very often this a decision on how to route, on where to route the calls to the LLM is not done on the application level, but it's done on the environment level. So in this case, for example, the environment can be your cloud environment, and you're deploying that proxy server. It could be Light LLM, for example, or it could be LLM Studio with some extra logic on how to write LLMs based on some either parameters that it's getting or some techniques that Gabriel is going to show. And that that unit is going to route it to either Anthropic, OpenAI, or to the right LLM. So that's an architectural decision that we recommend customers to do, not manage this routing on the application level, but think about it on the organization or environment level. So Gabriel, I want to bring it back to you because I can only speak high level. If you have this smart router, how can you actually implement a logic about, can you give me some examples to how you can implement a logic in that router that's going to reduce the cost of LLMs? Because again, we are in an AI for less webinar.
Yeah, thank you. So let's just take a small peek inside the black box of these routing services. Of course, we don't know exactly what they're doing internally, but let's have a few guesses. So one of the patterns that you can implement for this use case is cascading. So the idea is that you define a scoring model, and this is very common in like fine-tuning workflows and a lot of LLM workflows, where you train a model to either match your like the preference of your users, or you define some kind of hallucination likelihood score, and you create a threshold for accepting an answer. So let's say you go to a 7 billion parameter model, and then it's not accepted. So you go to a bigger model, and then if it's accepted, you just stop and it's done, and you saved a bunch of money. If it's not, in the end, you get to whatever it's the most expensive model in your list. So it could be GPT-4. You could have less tolerance for expensive models, but this is the idea behind it. If you
And I think one of the things, sorry to jump in, but one of the things that's really important here is that you're starting with a smaller model, right? Because it's significantly cheaper to go to the smaller model, like orders of magnitude cheaper. So like 1% or even less than 1%, to try it with a smaller model before going to the bigger one. So the opportunity of saving is significantly bigger than what you would already know that you're going to pay. And that is great. But, and there's a huge but here, how are you going to know that you can actually go, how can you get that like score is enough or not enough? So are you going to crash against the user and going to show the results? And then if the user is not happy, you're going to upgrade to the bigger model? Because, Cascade has this problem. So how can you give me an example, Gabriel, to how would you decide to go upwards?
So you could use, depending on what the model outputs, you could, for example, use the probabilities of the tokens that were output and use this as a hallucination metric. Or you could train your own model for this specific use case. And this is something that is quite common. Of course, you need a bit more effort and a bit more data, but for example, at the scale of the Martian router, it certainly is worth it to do it, right?
I
So
saw another one which was interesting. So it was saying, assuming that the LLM was giving a task, and my task has something to do with accuracy. So the more the LLM is confident in the results are going to come the same. right? So let's say I'm asking the LLM several times the same question, and then it's going to provide the same answer. So I can know that the LLM was confident in giving me back this answer. So if I'm getting the same answer multiple times, then I know that I'm okay. And it's actually more profitable to call, or it's lower cost to call Mistral 10 times than to go to GPT-4 one time. So you're calling it enough time to decide if you got the same result again and again. And if the variance in the results is too big, then you're increasing. So that's like a good example of how variance in the responses can be the key to go to a bigger model.
Yeah, so it's a really smart way to do it. And as long as your models are orders of magnitude apart in terms of cost, it's always worth it.
Mhm.
So another approach to this problem is to simply have either on the product side, like we saw with Notion, or another model, smaller one, decide which topics should go to each type of model. So if you have a Spanish model and an English model, you can very easily detect which language the question was in and do this routing. And or if you have a model that classifies how hard the problem is, or if it needs to be forwarded for GPT-4 for a certain reason, it is. But if it doesn't have to, then it isn't. And as long as you get some like 10 to 20% not going to GPT-4, it's already worth it. And these are the main two ways to do it. But these days, with more bleeding edge tech, we see this routing logic being embedded into the models themselves. And this is the case for most of the most recent models. So GPT-4 is allegedly a mixture of experts model, which is what they call embedding this into the model. And like Mixtral is doing this, Meta is probably working on this as we speak. So it is the future of LLMs. But what this essentially does is every layer of the model has different experts. And at every layer, you decide which expert should address this specific problem. Usually you go to more than one, but that's kind of besides the point. But this allows you to, in a 100 billion parameter model, only run 10 billion parameters. So it's like 10x in terms of speed. However, current architectures can't have the models outside of memory right now. So these models still take up too much memory as if they had 100 billion parameters. So what I'm saying here is that in the future, these architectures for routing could be obsolete, but so far it doesn't look that way.
Thanks. So we promised people to talk about architectures. So if we want to talk about architectures, we want to talk about the two design patterns that we're seeing these days. There are more design patterns like agentic workflows and chains that we're not going to discuss about. But we chose to focus on very two in which the way that you define the trade-offs is going to very much define the architecture and have a huge impact on the cost. And of course, talking about a big question that is being raised of RAG versus large context. And in order to address this question, we came up with a good example. So at least in my opinion. And we gave this example, I think, more than a year ago in a webinar that Gabriel and I did. We gave it the same name of the A16Z article, Emerging Architectures of LLM Applications. You should probably watch it. It has about 15,000 views. We defined something called the Harry Potter dilemma that we a little bit developed a little bit. So let's take one of the Harry Potter books, right? One of the Harry Potter books cannot go into the context of one LLM, and we want to give the LLM two tasks on the. Sorry, it can, but not necessarily. We want to give the Harry Potter book two different tasks, which can be LLM tasks. In one of them, I want to ask, which candy did Harry Potter eat on the train to Hogwarts? Right? This is a question answering task that AI can do. And on the right, I'm going to ask, tell me the story of the book, let's say the Philosopher's Stones from Ron Weasley's perspective. Now, that is a rewrite task of AI. And both of them are very legitimate tasks to give to an LLM. So This one is going to help me demonstrate the concept of using RAG versus large context. And let's start with RAG. So in the first question, first I'm asking which candidate Harry Potter is on the way to Hogwarts. I don't need to read the whole book, right? If I can find the relevant parts, maybe the train to Hogwarts, I can identify that this section is talking about the train to Hogwarts, maybe by identifying the word train in the chapter and then just bringing that chapter, then I can narrow down the amount of data that I'm sending to the LLM. And that is effectively the idea behind RAG. So the idea behind RAG is that you're putting a query, for example, what candidate Harry Potter it on the way to Hogwarts, and then you're sending it to a retrieval system. And the retrieval system can do retrieval at significantly lower cost. For example, Elasticsearch, right? So Elasticsearch can find keywords and find the word train at a significantly lower cost than running an LLM on top of the whole data. And then only the relevant data is going into the LLM together with the question, the original question that the user asked. You're putting it in and you're getting a generated result. And this is something, for example, that we implemented together with Panaya on their Seymour. A lot of these cases that you see of assistants or usage knowledge corporate knowledge chatbots, they not necessarily need to have all of the information of your organization. They don't need to be trained on all of the information of your organization or being fed with all of the knowledge of your organization for every question. You can go and find the relevant documents before, fit it into the LLM and get proper results. The impact of it, like this one is from the Gemini 1.5 Pro technical document, is that if you use all of the tokens, you can pay a few dollars, maybe $50 in this case, allegedly. And then if you're only sending a few data, like less data, then you can save a lot of money. Now, this is a great design pattern. And a year ago, everybody thought that RAG is going to be the solution for all of their problems. But it turns out that it is not the case. But before going to like this RAG, Gabriel, a few techniques that you can give me about still optimizing and reducing the cost of RAG.
Yeah, so we talked about RAG itself as a cost-saving technique, but I feel like a very important point is to apply what we just talked about into a RAG system so that we can see what it really looks like to start like saving money on different parts of these systems. So let's say you have a simple chatbot that answers questions about a database of products you have internally. So let's say you're Apple and you're doing questions about iPhones, right? So you just do what every RAG application does. You go to you use OpenAI embeddings. You use these embeddings to retrieve on a vector database. You send the documents you retrieve to GPT-4, and you have an answer. No big deal. It's really expensive, really slow, but it works. What we can do, and this is what we talked about before, we can just switch out the LLM, which is the biggest cost in this whole system, for a cheaper LLM. So let's say we have our own fine-tuned llama, we have a quantized llama, or another hosted service, whatever, we can just switch it off and then put in the llama instead, and you just save like 50% of the costs. However, in RAG systems, we have another variable, which is the embedding system. So embeddings, for example, from OpenAI out of the box are quite good, but they're not going to be tuned on your specific use case. And it's kind of like GPT models in a way. So what you could do is simply train your own embedding model, and you could use smaller models, so therefore making the whole thing cheaper and faster already. But also you can make it more relevant by training it on your data, so you would have better context, so you need less of it in the LLM, so you'll also save money this way. Another thing you can do is to compress what you retrieved. So let's say you retrieved 10 products from your vector database, and they're not all relevant, but if you send this to GPT-4, it will probably be able to ignore them and just not say anything in the answer about them. But you can also use a smaller model to just filter out what's irrelevant and summarize what's relevant so that your final big smart LLM gets as little tokens as possible so that you save a bunch of money. So in essence, by using these techniques on RAG systems, you can have less context, but in a good way, so it's cheaper. you can have more relevant context, which allows you to send less of it, which makes it cheaper. And you can have custom embeddings that are both faster and cheaper, like the embedding model itself, but also more accurate at retrieving stuff. So you can have more relevant context, therefore shorter context, so therefore cheaper. So all these things work together for a really efficient RAG system that you can actually provide value with.
Yeah. So we said in the beginning, we're going to use the Harry Potter dilemma for this. So in the Harry Potter dilemma, if I asked you which candy did Harry Potter eat, then you only have to find the relevant information. What happens if you really have to use all of the context, right? So if, for example, I need to rewrite the whole book to tell the whole story of Harry Potter from Ron Weasley's perspective, then effectively, and assuming the LLM was not trained on Harry Potter, so it doesn't know Harry Potter, right? Because this is introducing a bias for itself. But you actually have to put in all of the story, because otherwise you cannot just look for the parts that Harry Potter or Ron Weasley is there. You're going to miss out on the information. So uh, sometimes you do have to understand that you are going to use all of the large context for these cases. And, Google came up with their model recently, actually not recently, quite a few months ago, Gemini 1.5 Pro. And initially it was for 1 million tokens, and later on it included 2 million tokens. And this stuff can actually accommodate entire books inside, which is great. Of course, you're not going to send all of the information, but there are these tasks in which if you do send all of the information at once to the LLM, you are going to, that's the only way for you to actually answer the questions or perform the task that you had to do before, that you have to do. But like we said, it's going to be expensive. So how can you still reduce the cost? And this is something quite recent. So think about the case of the Harry Potter dilemma that we showed, in which you want to ask multiple questions that require Harry Potter book to be put in entirely to the context. Very often, if you are building an LLM application, the task is going to be repeating itself. So you're going to use a lot of tokens again and again by sending the whole of the Harry Potter book again and again. And then what would change is maybe just the question that you're going to ask on top of that. So one time you're going to ask, tell me the story from the Hermione's perspective. And one time you're going to ask it from Ron Weasley's perspective. So what if you can just cache that result, right? Every time use the same cached result of the entire Harry Potter book and just query the LLM in a different way. So apparently, since last month, this is possible with Gemini 1.5. So if you're working with Gemini on Google, you are capable of deciding on which parts you want to cache. And then in the original setting, every time you're sending a prompt plus a context, and then you're, the LM is going to do input processing, and it's going to do generate a response, and then it's going to do output. In the case of caching, what will happen is your cache is going to go directly to the generation of the response. So you can actually have a mini RAG within the LLM, which is great. And there is this case, you have the name of the writer on Medium that already show that it can achieve some cost reduction. It does not achieve full cost reduction. You still pay for the generation. So you're not going to see 95% cost reduction, but you are seeing nice numbers, especially compared to like not doing optimization at all. So caching is definitely a very interesting idea to follow. And we are sure that we're going to see this being implemented by other vendors as well. So I want to bring it back home and try to wrap up what we've seen. Effectively, what we wanted to convey to you is that AI in AI, cost is a dimension, and it is a dimension because maybe you will have a competitor developing an application with similar capabilities, but because they're doing cost optimization, they're going to sell it for less. And if you think about the Klarna case, the quality of the LLM and the cost of it is something that is going to be a differentiator between solutions, right? You're doing it to achieve efficiency, so the efficiency is inherent to your model. And this is something you don't always see in other applications, because sometimes, you know, cost is not the main differentiator between applications. So we do think that cost in AI applications is more important than traditional software. And some of the advances, some of the cost reduction is not going to be thanks to you. Some of the advances are going to be thanks to companies like NVIDIA coming up with new GPUs. Some of it is going to be thanks to OpenAI coming up with their new models, or some of it is going to be thanks to liquidity in the markets of startups that are going to give you to use free products to accumulate to gain market share. But what you can do is either use local optimization, right? Think about reducing the size of your LLM or optimizing your prompts, or doing some architectural decisions, right? Reduce the or configure the architecture in a way that is more suitable for your use case, and kind of navigate the cost versus fitness of your whole solution, so you'll have more optimized results. What we at least noticed is you're either typically going to give up, in order to reduce cost, you're typically going to give up either on breadth. So your LLM is going to be less generic, it's going to be more specialized. And that goes to the question of fine tuning. We didn't mention fine tuning, but it is somewhere there between, you know, making your LLM reduce size and then make it more specialized as a specific task. Or you're going to accept that the LLM is going to be just more stupid, and to that we call depth. So we hope that you enjoyed this webinar and you learned something. If you did, feel free to sign up to our meetup group. We will post this one on YouTube, and everybody who registers is going to get a link to this. And that's it. We want to thank you all for coming, and see you in the next webinar.